Okay, so let's compare with the materials property Young's modulus with different types of materials. Okay, therefore, if we compare with the Young's modulus with different type of materials like metal alloy and ceramics and polymer and composite. So what the difference between them? So we can see that the Young's modulus of metal is lower than that of ceramics, right? And it's higher than polymer, and wow, it's quite similar to that of the composite materials, right? So from this comparison between the different type of materials, we can realize that the metal is a more ductile, right? Metal or alloys is more ductile than that of the ceramics. The ceramics. Okay, so we can select the different Young's modulus corresponding to our applications, right? For example, we need high hardness for some surface coating or surface strengthening applications. Therefore, we can select the ceramics, right? Because whose Young's modulus is the highest one. It's the highest one. Okay. However, if we need this mechanical parts or components has the very high strength, but ductile. Of course, the first choice is the metal or alloys, right? Right. And if some applications such as the toys or some some parts or product which doesn't need high strength. Okay, so, and what I need is the reduced cost. Therefore, we can choose the polymer, right? The plastics, right? The plastic. And if we need the function of these products are like lightweight and high strength, and of course we can use like a carbon fiber or carbon fiber composite materials, right? Because like the relatively high Young's modulus with high strength and low density Okay. Okay, let's compare the yield stress with different type of materials. So what we can find that is the metal and alloys has the highest Young's the yield stress than that of ceramics and polymers, right? And polymers. Okay. So that means the metals are more ductile, right? Compared to ceramics. Okay, compared to ceramics. Okay. Okay, so let's compare the tensile strengths with different type of materials. What we can figure out is the metal, the tensile strengths of metals, while similar to that of the composite, and higher than ceramics and polymer. Okay, well, one characteristics of metal is that when the applied stress higher than the tensile stress, the necking occurs, right? The metal necking occurs. Okay, and but for the ceramics, for ceramic, there's no any necking phenomena. Okay, for ceramics, of course, for polymer or the composite. Okay, therefore we can use tensile stress to to define which stress to trigger the necking process of metals. Okay, metals. Of course, for ceramics, are brittle, right? It's brittle materials. Therefore, they're gonna be fractured immediately, or without any warning, without any plastic deformation. Okay. Okay, so let's look at the stress and strain curve by the tensile test. Okay, so we can figure out several materials properties or mechanical properties of metals from the stress and strain curve. The first one is what we already mentioned, is the slope. The slope of the stress and strain curve within the elastic region. Okay, the E. And the tensile stress, ultimate tensile stress, UTS. Okay, UTS. Therefore, when the apply stress is higher than the UTS, that means the necking occurs. Okay, that means the necking occurs till it's fractured. Okay. And the metals, for the metals, the tensile stress occurs when noticeable necking starts. However, for polymers, the tensile stress occurs when polymer backbone chains are aligned and about to break. Okay, so as we know, the polymer chain is like this carbon chain, right? It's like this. Okay, it's like this. Okay, it's like this. Or it may be random. Okay, maybe like this. So when we apply a tensile stress, when the applied stress reaches this tensile UTS, this polymer chain will be aligned. Okay, if this the stress, applied stress. Okay, this polymer chain backbone chains are aligned. Okay, so we can compare with the brittle and ductile materials with their tensile test. So we can compare, for example, for this one is the materials A and this materials B. From this stress and strain curve, we can realize that the materials B is more ductile, right? It's more ductile. And materials A is brittle. Okay, it's brittle. And the area under the stress and strain curve, is called the toughness. It's called the toughness. The higher toughness means that these materials can absorb more strain energy. That means these materials more capability to absorb the energy for deformation. Okay, deformation. Okay, so and for materials A, you know that they cannot absorb any strain energy, right? So when you apply the stress to deform the brittle materials, it will break immediately or suddenly because they cannot absorb the energy, right? And you apply a high energy to deform it. Of course, these brittle materials must be broken immediately without any warning. Okay. And how to define the ductility? Oh, let's say, oh, this material is ductile and that is brittle. So how to define the ductility? The first is elongation rate. Okay, it's called elongation rate from the tensile test. Okay, so divided by the plastic tensile strain at failure. Okay, the failure. It is equals to this elongation rate equals to the final length minus the initial length divided by the original length. Okay, so we can just measure the length after fracture, okay, and the just calculate the difference between the final length and the original length divided by the original length, right? Of course, you from this stress and strain curve, you can realize that this material has the higher toughness. That means it can withstand the deformation. It has the higher capability to absorb the energy for deformation. Okay. And the other way to define the ductility is the area reduction or reduction area. Okay, the same. We measure the cross section after fracture, right? After fracture here. Okay, therefore we can calculate the difference between the original area and the fractured area divided by the original area. Therefore, we can figure out it's called the area reduction rate. And the materials has the higher elongation and area reduction rate means that it is ductile, right? It is ductile. Therefore, we can compare with different materials with their elongation or area reduction rate to distinguish their ductility. Okay. Okay, so let's compare with three types of materials. Materials A, B, and C. A, B, and C. So let me ask you a question. That is for the car, the frame, and the metal sheet or the engine cover. Okay, so for making the car, which materials is more suitable for manufacture a car? A, B, or C? A, B, or C? Of course, right? Of course, the metals is the most suitable materials for manufacturing a car, right? Why? Because it has the highest toughness, right? It has the highest toughness. So let's think of this way: if the car is made of the from the materials A, what's gonna happen when you sit in the car and drive? When the accident happens, so what's the consequences if the car is made of the materials A and you sit inside, you are the driver? What's going to happen when a serious car accident happens? The car will become pieces, be crashed in pieces, right? And maybe your flash body will become pieces, okay? Will become pieces, okay? On the other hand, if this car is made of the materials C, what's gonna happen if a severe car accident happened? And you are the drivers. You are the drivers. Okay, you're sitting in the car, which is made of by the material C. When the car accident happens, what's the consequences could be? And the consequences could be because material C has a very small toughness, right? Small toughness. So what kind of materials belongs to material C? Like a rubber, right? Like a rubber. Okay, so when the accident happens, the drivers will be deformed. Okay, will be deformed. as the same shape as that of the material C, right? Okay, and after that, after the accident, the car will return to its original shape, and you, the driver, will remain the same shape, the same shape. That means you, the driver, will be deformed, and the car will return to its original shape. Okay, so if you choose the materials A or B to make of the car, when the car accident happens, either you will become pieces, you will be crushed like pieces, or you will be deformed. You will be deformed, okay? Okay, so let's look at the other terminology called resilience. I already mentioned that the area under the stress and strain curve is toughness, right? The higher toughness means this material has a higher capability to absorb the strain energy, okay? As for the whole area under the stress and strain curve, and the resilience is the ability of the materials to store energy within an elastic region, okay, within an elastic region. Okay, therefore we just calculate the area below the unit stress. Okay, unit stress. Okay. Similarly, we can assume a linear stress and strain curve of this stress and strain curve that simplifies to the energy to be stored in the elastic region equals to half times unit stress and unit strain. Okay. Okay, so next, the other materials property is called hardness. And hardness is the resistance to permanently indenting the surface. Okay, if this material is a high hardness, that means it provides a high resistance to what? To the indentation. Okay, to indentation. Therefore, the large hardness means the higher resistance to plastic deformation or cracking in compression, and it has better wear property. Okay, you have a wear property. To be a mechanical engineer, you must have the you need to have a concept in your mind. Okay, you don't have to remember the precise number of hardness. However, you need to have this basic concept in your mind. You can tell which type of materials is harder than different type of materials. Okay, for example, say, oh, the cutting tool. When if there's a mechanics just ask you, oh, whether I can use the steel knife to cut or to machine an aluminum tube. While you're an engineer or you're a scientist, of course you will know that it is impossible, right? You have to tell him, say, okay, you cannot do that because you're simple aluminum whose hardness is much higher than steel. How can you use a lower hardness cutter to machine a high hardness sample, right? It not make sense. And you need this sense. You need this concept of those hardness. Okay, so you must know, oh, the alloy, aluminum alloy, it must have the lower hardness, right? It must have the lower hardness compared like to the steel. Okay, and you have this fundamental ideas about the nitride or the ceramics, the silicon or the carbide. Always has the higher hardness than most of the metal. Okay, so you need this very fundamental concept in your mind. Okay. Okay, there are different hardness test technique like Brunel or Vickers, Noob, or Rockwell, and so on. Basically, they use different shape of the indentation tip, and we measure the dimension of the indented area, and we calculate a specific volume to define its hardness. Okay, to define its hardness. Okay, so let's look at the true stress and strain. So when I already mentioned that the sample, a rod or plate, when the tensile test applied to those samples, and we just keep pulling till it fracture. And this stress and strain curve we measured is called engineered stress and strain curve, but not true stress and strain. Why? Why it is not true? Because what? Because when tensile testing, the cross-section area keeps reducing, right? Keeps reducing. That means the area keeps changing. But for the engineering stress and strain curve, the cross-section area is a constant. A naught is a constant. However, for the real case, the cross-section area is not a constant. Okay, it's not a constant. Okay, and the true stress equals to force divided by the area, which is instantaneous change. Okay, and the true strain equals to natural log of the length, instantaneous length divided by the original length. And there's a relation between the engineer and the true stress and strain. Okay, and this is the relation. True and engineer. True strain and engineer strain. Okay, therefore from this figure, from the stress and strain curve, we can measure engineering is this blue one. Okay, and for the red one, we can convert it from the engineer stress and strain curve. Okay, and maybe you would ask, well, which one? I mean, the engineer one or the true ones? Which one is more useful or more functionable for the industrial application? As what I say, the true stress and strain are difficult to measure. Okay, it's hard to measure its cross-section change in time. Therefore, those mechanical property that we already defined, like Young's modulus, tensile stress, and so on, is based on the engineering stress and strain curve, but not true stress and strain curve. Okay. So let's look at the engineering and the true stress, how to convert it between them, how to convert this true and engineer. Okay, how to convert it between these two. Okay, so remember the notation is the engineering stress, engineering strain, and true stress and true strain. I just used a different notation because I found this data from different sources. Okay. So we can calculate the true strain by the engineering stress and strain. Okay. So for the true strain is equal to the force divided by the instantaneous area, right? And this area keeps changing during the tensile test, right? And we know no matter you're concerned the engineer or true strain, the volume is a constant, right? Your sample is constant, no matter it's true or engineer, doesn't matter. Okay, it's constant. Therefore, the volume between them is the same, right? Therefore, the volume equals to the instantaneous area times the instantaneous length equals to the original area times the original length, right? And the true stress equals to force divided by instantaneous area, and this instantaneous area equals to this term. Okay, this term. Okay, and for the true for the strand equals to the instantaneous strength minus the original strength divided by original length, sorry. So instantaneous length divided by the original length divided by the original length. You get the strength. Okay. Okay, and the strength equals to L over L naught minus 1. Okay, okay, and this term can be plugged in here, right here, right, and this term equals to what? 1 plus epsilon strength. Right, I just move this minus 1 to this side. Okay, therefore we can figure out the engineering stress equals to F, the force, divided by the original area times 1 plus epsilon. And this term equals to engineer stress, right? Therefore, we can figure out the engineer stress, and the true stress has a relation of 1 plus epsilon. Okay, just a very fundamental, very simple mathematical calculation. Okay, so let's look at the true strength equals to the integration from L naught to L. dl over L. And we can take the integration of this term. We'll get a natural log of L over L naught, right? And we already know the L over L naught equals to this term, right? And we just plug this term here. Okay. Therefore, we can get the relation between the the instantaneous length equals to 1 plus epsilon times the L naught, right? Therefore, we can find the relation between the true strength and the engineering strength. Okay. Is that clear? So this term we'll get it's the same, right? L over L naught equals to 1 plus epsilon, and just this term to plug in here, right? And we'll get this term. Okay, so that's a very fundamental calculation. It's not difficult, right? Okay, so let's look at the true stress and strain curve. Okay, and we can fit this true stress and strain curve from this, right? We already know how to convert it from engineering stress and strain to true stress and strain. Is that clear? Okay, and we can fit that curve to find an equation. Okay, to find an equation like this. Okay, like this. Okay, and I already asked you a question, is that for this stress and strain curve, okay, it's true stress and strain curve. Okay, so the yielding stress, the second yielding stress is higher than the original one, right here. The reason why is that the dislocation increase during the plastic deformation, or we can say the dislocation density increase during the plastic deformation, okay, to enhance its yielding stress, okay, to enhance its yielding stress. Okay, and if the curve fit to the stress and strain response, I mean the true stress and strain, we'll get the equation like this. Okay, therefore we get a true stress equals to constant times true strain with exponent parameters. Okay, and K means materials property. K means materials property. Okay. Okay, so we can convert the engineering stress and strain to true stress and strain, right? And we already mentioned that, and we find and fit by fitting to figure out this equations. And there are two constants. One is K, is called the stress coefficient, the materials constant. N is already mentioned, it's hardening exponent. Okay, so how to get these constants? How to get these constants? How to get the constants? Of course, K equals to the slope, right? Of the true stress and strain curve in the elastic region. And what's the definition of the number of n? Okay, so let's look at this. So when we converted the figure, the stress and strain curve, from engineering stress and curve, okay, and we get the figure C, right? The figure C, and we take the log. We take log of the true stress and strain curve. We can convert it to a linear relation. Okay, so we can convert it from the engineering stress and strain curve to the true stress and strain curve, right? Like this. And we take the log graph, we can convert this true stress and strain curve to a linear relation. Okay, to a linear relation. And the slope of this linear relation is n. Okay, so maybe we can have different linear relation. Okay, right? Like this, whatever. And they have the different slope, right? Different slope. Okay, so what's the definition of the slope, or what the definition of n here? If we have a higher n, what's that mean? Or lower n, what's that mean? It's here. The higher slope, the greater is the strand hardening capacity of the materials, and the stronger and harder it becomes as it is strand. Therefore, if this material has the highest slope, that means the higher volume of N, that means it can withstand, it has the higher capacity when we strand hardening this materials, you have the higher capacity to withstand this plastic deformation. Okay, after strand hardening, and this materials has the higher hardness and has the stronger strengths than others. Okay, therefore we can use these characteristics, right? We can do the tensile testing and to find the engineering stress and strain curve and convert it to the true stress and strain curve, right? And plot the log graph, and to find out the slope of this linear relation. Okay, therefore, for some product or for some materials, we can get a different linear relation of this true stress strain curve. Okay, so we can get this and this and this, right? And this. So this figure can be an index for our product. For example, we have this alloy, some product made of some alloy with different process, right? With some different process, and we can plug this true stress and strain curve to figure out the volume of N, right? And when we know the volume of N, okay, we can realize, okay, this process, this alloy made from this process can have the higher value of N. Okay. Okay, so let's see. Let's just look at one example for a design. Okay, for design, machine design. Okay. So the meaning of design is that we have to design its uncertainty. That means we don't push the limit, right? We need some tolerance. Okay, we need some tolerance, right? So the safety factor, the idea of the safety factor is a value or is an index to prevent to reach the limit. Okay, and this safety vector or vector of safety depends on different applications. Okay, therefore the working stress, okay, the real working stress in industry. Okay, you must know the working stress, okay, because you're an engineer. You must know the working stress, and you must know the yielding stress, right? If you use the already metals or alloys, you must know the yielding stress. Or if you use some materials you don't know its yielding stress, well, you just do the tensile test, right? Tensile test. And the N is factor of safety. Okay, factor of safety. Okay, so just look at a very simple simple example, like to calculate a diameter to ensure that the yield does not occur in 1045 carbon steel rod, and use the safety vector of 5. Okay, therefore we have the carbon steel rod like this, right? Therefore we can figure out its unit stress. We can find its unit stress. And it's tensile stress because it's materials property, right? The unit stress and tensile stress are materials property. Okay, and we apply a force, right? We apply a force. Okay, and we know we have to calculate the diameter of this rod, round rod. Okay, and the working stress equals to the force divided by area equals to the unit stress divided by the safety factor. If the safety factor equals to 5, and you can figure out its diameters, right? You can figure out its diameters. Okay, so do you think the safety factor 5 is large or small? Well, from a personal perspective, it's quite large. Okay, it's quite large. However, it depends on the application, your industrial application. Okay, as I already mentioned here, the N is between 1.2 to 2. Okay, it's totally depends on the lifetime you want to use, or your working stress. Okay, for example, if the safety factor is smaller, that means this product might be used can use in maybe 10 years. However, if the safety factor is 4, that means maybe this product can be used for 20 years. Okay, but you have to think of the other way, is that if this product can be used in 20 years or longer, how can this company make money? If this product can be used 20 years, well, maybe I don't want to change. I can use 20 years. And this product can be used in 10 years or shorter. Okay, so maybe this family or some customers will change a new one in 5 or 10 years. Well, so there are a lot of things you have to concern for the machine design, not just for safety. Of course, safety is the first priority. Is the first priority. However, there are a lot of issues you have to concern to be a mechanical engineer or the materials engineer. Okay. Okay, so the course here will be ended here, and I will provide you the phase diagram course in next chapter. Okay, so see you next time.